Back to the part two of plate girder design. Like I mentioned in the last video that we have 14 steps, 14 design steps while designing any plate girder. So basically, in this video, let's try to cover the first five steps, that is design constants, design forces, design of wave, design of flange, classification of flanges, and if we have time, we are also going to see if we can cover the check for bending stress. All right, so let's see what we have in terms of our problem here. All right, so the problem is given as we have to design a welded plate girder of 24-meter in span. Like I mentioned in the last video, plate girders are usually required where the span is quite high and that generates a huge moment. It said that the plate girder is laterally restrained throughout and it supports a uniform load of 100 kN per meter throughout the span, exclusive of self weight. That means we have to include its self weight as well. Design the girder without any intermediate transverse stiffness. So I didn't mention in the last video. Stiffness are usually like two types. Two types of vertical stiffness are there: intermediate stiffness and end bearing stiffness. Right. So intermediate stiffness are provided where the wave needs support in case of buckling uh, at the at certain intervals. Okay, but end bearing stiffness are usually provided near the support where there is huge amount of shear force that is being transferred to the column, right? So in this problem we have been asked to exclude the design of intermediate transfer stiffness. We only need to consider the end bearing stiffness. The steel for the flanges and wave plate is of grade Fe410. Design the cross section and the end bearing stiffener and the connections. Okay, so that's the problem is all about. Uh, so the first step, that is design constant, we need to write down what are the as per the given conditions, the grade of steel, Fu, Fy, uh, what are the partial factor of safety, and the constant. So you simply write it down and then uh, going to the next step, that is the design forces. So your superimposed load is given as 100 kilonewton per meter in the problem. So you simply multiply it with 1.5 to get the factored superimposed load. One assumption is taken here, it's a thumb rule. Self weight of the plate girder, it's taken in terms of the superimposed load. It's a thumb rule to use WL by 400. W is the service load that is coming here, that is 100 kilonewton per meter. So you simply take the self weight of the plate girder and it comes out to be 144 kilonewton. All right. So if you distribute it, if you take it as a UDL, divide it by 24, and it's come to be 6 kilonewton per meter. And simply adding up and finding the maximum bending moment, WL square by 8 and WL by 2 to find the maximum shear force. So that's all about the design forces. In the next step, we find out the design of wave. Optimum depth of the plate girder is given using this formula. All right, and one thing we need to know here, uh, there are specific requirement clauses while doing design of the beam, right? So here as well, there are certain serviceability criteria and flange buckling criteria are provided in the IS 800. So I'll simply take you to there. Clause number 8.6 in the page number 63, if you go there, it provides the serviceability requirement of wave stiffness. Uh, so if you take stiffness and if you don't take stiffness for different conditions, there are different serviceability requirements are there. So when transverse stiffness are not provided, the limit is given as d by tw should be less than 200 epsilon. So in this case, we are not using intermediate stiffness. So I think this case will be applicable in case of us. And also As per the flange buckling criteria in the 8.6.1.2, we also have dy tw less than equal to 345 epsilon f square. All right. So these two conditions are used here from serviceability criteria and from flange buckling criteria. All right. Uh, so using all these things, since here you have to assume k, this k, uh, it should be around taken around 180, and they have taken that only. Assume k as 180, and then finally find out the depth, optimum depth of the plate girder as given here. All right. Let me go to full screen. Yeah. All right. So finding the depth of the wave here, and using the same formula, you can find out the TW, that is thickness, or maybe you can use this one as well. D by TW equals to 180. You can simply use that as well, and here it is coming out to be 12 millimeter. So what you need to do here, you find out D using this formula here, and then assume K to be D by TW equals to 180. Simply putting D as here, you find out TW. All right. So in this case, the wave plate turns out to be 1800 into 12 millimeter in size. So that's your wave plate. Now you are going to design the flanges. Okay. So like I mentioned in the previous video, shear is only taken by wave and moment is only taken by flange. So top flange and bottom flange combined will take the moment. So simply by using the formula mz equals to af fy multiplied with d, that is the distance between them, that is the lever arm here, and divided by gamma m0, the partial factor of safety. So if you rearrange that equation, mz equals to af fyd by gamma m0, if you rearrange it and write it in terms of af, you find this expression, and then simply substituting mz you have simply calculated before, the external moment, and you get this required amount of area. All right. So you simply found out the area, and then one assumption is there, uh, width of the flange you assume as zero point 0.3 times the depth of the girder, that is small, and simply you find bf, that is zero point 0.3 of 1800. So it comes out to be near about 540. You take it as a 560 millimeter just to be on safe, and using like you have found the area, so bf into pf will be equals to area, so you simply divide the area by 560 and you get the thickness that you require. So you obtain the flange dimensions by this method, so 560 into 50 millimeter flange plate. So now it's time to use the classification of flanges. So like simply you used the table, the chart in the last, in case of beam design, uh, you will use the same thing for classifying the sections, classifying the flanges. So if you do that, BITF, you get the section here as the flanges here as plastic. All right. So I think we have 1 more minute. So let's quickly cover up the next step, check for bending strength. So simply, since only flanges are taking the uh, required moment here, so you simply calculate the plastic modulus of using the flanges only. This only calculates that plastic modulus here, and simply using the formula for moment capacity, uh, as similar to the beam, you find out the moment capacity of the plate girder, and in this case obviously which turns out to be greater than the external moment and which is safe. All right. So for in this video we are going to discuss up to this point. Next video we are going to start with shear check of the wave.